Hello everyone, welcome to the problem solving session from the design of welded joints or eccentrically loaded welded joints. In the previous video, we have seen the procedure for doing the same. So here we will solve this one. So here a steel bracket is welded to the structure and loaded by a vertical load of this 35 kilonewton. Here the load is not actually parallel or transverse with respect to the fillet weld provided. So here this load is called actually eccentrically loaded welded joint, because if you are considering this weld section, here also I am showing, then the CG of the weld section will be coming somewhere here and will be exactly locating the same point for this problem. So here the CG will be acting, that means at this point, but the load is acting through this point, or the line of action of load will be like this. So it is not passing through the CG, and thus load is known as eccentrical loads. And here we need to find the size of the weld. Size of the weld means we need to find the value H, size or leg of the weld, and here the allowable shear stress on the weld is given, which is 90 megapascal. And we have seen that the first step in this procedure will be to find out the location of the CG. That means where the CG will be lying. It will be lying somewhere here, so we need to locate this point, and that can be obtained from the data book. So in page 96 for the design of welded joints, here you can see the cross section. Here we are having this kind of shape, and that can be referred to this table where you will be finding the matching figure. So here the shape is given, and here I have enlarged to the same thing is can be seen here. And here one mistake is there for finding or locating the CG. Here this will be symmetrical with respect to x-axis, so and the another line is here, so the CG will be coming here. So in order to locate the CG, we need this distance ny, and the equation for ny is given as n square by, this is actually 2n plus m instead of 2 into n plus m. There is no bracket actually, so this is actually n square divided by 2n plus m. So we need to locate the CG like this. So we can find the value of this distance, that is here. This distance is ny, which is equal to n square by 2n plus m. In this problem, the value of n and m. N is the distance, which is this. N is this distance and m is this distance. So 120 and 240. So here you can substitute 120 square divided by 2 into 120, which is 240 plus another 240. So this value you can evaluate, and if you are solving, we will be getting the ny as 30 mm. So we have located the CG. So the same thing will be taken to this figure. So CG will be coming here, and this distance we have obtained, which is 30 mm. And then this is known as eccentricity, which is the distance from CG to the line of action of load. So here we are having a length of 480. This is 120. Then this is 30. Then this distance will be 120 minus 30, that is 90. And this 90 plus this 480 will be giving you the eccentricity, which will be 570 mm. So the eccentricity value is 570 mm. So first we have evaluated we have located the CG, and then we have evaluated the eccentricity, that is the distance from CG to the line of action of load. Now we will be transferring this load to the CG location. That means here we are having the load acting at this point, but we need to transfer this load to this point, that is CG. For that we will be considering an equal and opposite forces, and these two pair will be creating a moment or couple, which will be creating, or which is known as torsional moment or torque about this CG. So the next step is to transfer the load to CG. So we will be having the load of 35 kilonewton magnitude, which is a load P, I can call it as. It will be acting as a direct shear load for the weld section, and the effect of same will be taken later. Along with this, a couple or torque is also acting, and that value is P into E, which is 35 kilonewton or 35 into 10 raised to 3 newton into eccentricity is 570 meter or 0.57 meter. 570 mm or 0.57 meter, and that value you can evaluate. And the effect of this torque will be to produce another torsional shear stress known as secondary shear stress. The same thing also will be evaluated later in this problem. So now we need to take the effect of this direct shear load and this torque on this weld section to find the resultant shear stress. That is our next step. So in this one we will be taking the effect of the direct shear load. That means here we are having the CG. Here we will be taking only the effect of this direct shear load. In this case, then we will not be having this force here. Then the 35 kilonewton will be acting at this point, and this will be taken by the entire weld section. So this force is acting in the same plane carrying the weld. So this will be acting as a tangential or shear load for this one, which creates shear stress known as direct shear stress, which we will be calling it as primary shear stress. So now we are having the finding the effect of P, and this will be creating the shear stress, primary shear stress, and we will be notating it by tau 1. This is equal to the load by shear area, and the shear area will be calling it as A, and we are having the load is equal to 35 kilonewton, which is 35 into 10 raised to 3, and area is, if the size of the weld is HT, we have already seen the throat size, which is represented as 0.707 into H, and this weld is running over a length of 120 plus 240 plus again 120. So then the throat area will be equal to HT into length of the weld. This is equal to 35 into 10 raised to 3 into HT. I will be representing as 0.707 into H. This H is actually the size of the weld, which is the unknown that we have to evaluate at the end of this problem. And again into length is, we will be representing in mm, 120 plus 240 plus again 120, which will be 480 mm. So if we are simplifying this one, we will be getting a value with the H in the denominator, and the numerator value will be equal to 103.14 divided by H. This is actually our primary shear stress. And if you are plotting the distribution of this shear stress in this weld section, it is uniform at all points. So here we can represent the tau 1A, here this will be tau 1, here this will be tau 1. At all points the effect is uniform because it is distributed uniformly at all points within this weld section, and this is the effect of load P or the primary shear stress. And now we will be evaluating the effect of the couple acting about the CG. Here we are having the CG, and about this one we are having the couple of magnitude P into E. So because this is a couple or torque with respect to the weld section, this will be creating shear stress across this weld section, and we are having the expression, general expression for the torsional shear. This is the effect of P into E we are taking, and we know that this will be creating a torsional shear, and that is known as secondary shear stress, and we will be denoting it by tau 2. So the expression for denoting the torsional shear stress is T by J into R, and we will be taking the value of tau 2. The maximum value will be taken. For this we need to take the value of maximum R. So R is the distance measured from the CG, and we need to take the point within the weld section where the distance R is maximum. If you are observing, this will be the point which is lying at the maximum distance from the CG. So this R we need to take. This is actually the R max or the capital R we can take, and we need to find the value of this R. We need to find this distance, and at this point the tau 2 secondary shear stress will be maximum, and the same to be considered for the design. So this will be the distance R, and we know that this distance is 30, then the remaining distance will be equal to 90, and this distance is half of 240, which is 120. So this value of R, which is actually the R max, will be equal to square root of 90 square plus 120 square. You will be getting this value as 150 mm. So we are having the value of capital R or R max for finding the torsional shear stress. Next, this torque is actually, we are having the values P into E, 35 kilonewton or 35 into 10 raised to 3 into eccentricity is 0.57 meter. So this much Newton meters we are having. Next is the J, which is the polar moment of inertia of this weld section. We are having the weld section in this shape, and for this weld section we need to find the value of this polar moment of inertia, for which we will be making use of the equation from the data book. Here we will be finding, we have already seen the required figure, and here from this one we will be getting the value of J or the polar moment of inertia. Here J is equal to HT is given, so same can be expressed as 0.707 into H into N and M value we are having. N is equal to 120 mm and M is equal to 240 mm. The same can be substituted here, that is 2 into 120 plus 240 the whole cube divided by 12 minus the n square into n plus 1. The same values you can substitute here, and finally we will be having a values in terms of H. If you are solving, we will be getting a coefficient for the J. The correct answer will be for J will be equal to 3.77 into 10 raised to 6 times H. So this J value can be substituted in this one. So here J is equal to 3.77 into 10 raised to 6 H. So with this we can find the value of the secondary shear stress. So secondary shear stress will be equal to torque, that is this value, into R max, which is 150 mm divided by J, this value. So finally we will be having an H in the denominator and a numerical value will be coming in the numerator, and that is 794.42 divided by H will be the expression for the secondary shear stress. And we need to obtain the direction of the secondary shear stress, and this is torsional shear stress which will be perpendicular to. So this point we are taking for an analysis because the secondary is maximum at this point. Then we are having a line joining this point and the center. Then the secondary shear stress will be perpendicular to this one and in this direction, because this is rotating or the torque is in the clockwise direction. So this can be represented as the secondary shear stress tau 2. So now we have obtained the primary shear stress from here, tau 1, and the secondary shear stress from here. With this we will be finding the resultant shear stress. So now we are having the primary and secondary shear stress, and one point to observe here, primary shear stress is same at all points. So any point can be considered as critical with respect to this primary shear stress. But in the case of secondary shear stress, which depends upon the distance from the CG and maximum distance is coming here, so this point is critical with respect to the secondary. If you are combining this one, the effect of both will be maximum in common at this point. So the same point can be considered as critical, and we will be finding the resultant shear stress at this point. So we are having the primary shear stress tau 1 which is equal to 103.14 divided by H in this orientation, and we are having the secondary shear stress which is in a direction. If you are having the CG here, then we will be connecting these 2 points, then it will be perpendicular to the CG. We are having the tau 2 which is equal to 794.42 divided by H. We need to calculate the resultant of this one. So the resultant can be obtained using the parallelogram law. Then we will be getting the resultant in this direction. So the diagonal of this parallelogram, this will be representing the tau resultant. So from the parallelogram law, if this angle theta is the angle between these two, primary and secondary, then the tau resultant will be equal to the primary tau 1 square plus secondary tau 2 square plus 2 into tau 1 tau 2 into cos theta I can take. So this theta we need to find. If you are observing, we are having an angle theta like this. So this line is actually perpendicular to this line, and this line is perpendicular to this one. So if theta is known, then the same value will be coming here also, because the angle between two lines and their respective perpendiculars will be same. So we need to find this theta. For that we are having this distance, that is from here to here, as 90 mm, and this distance, that is from here to here, as 120 mm. So if I am taking the value of tan theta, then tan theta will be equal to opposite side, 120 by 90. From here I will be getting the value of theta. So this theta, if you are knowing, then you can directly substitute onto this cos theta. So now I am having the primary shear stress tau 1 103.14 by H, tau 2 794.42 by H, and the value of theta. Then I can find the resultant. So if you are solving, you will be getting the value of resultant shear stress 885 divided by H we will be getting for the tau resultant. So this toe resultant can be equated to the limiting value or the allowable value given for safe design. So this maximum toe resultant should be less than the toe allowable provided, and we know that it is 90 megapascal. Here I am using the units of Newton for forces, Newton mm for the mm for the dimensions, and Newton per mm square for the stresses. So the torque should be used as Newton mm. That means in the previous step this should be actually 570 mm. So this should be Newton mm. All others thing I have the values I have obtained from the book. So this tau 1 and tau 2 are same. So from this we will be getting the value of 885 H, and this will be equated to 90. Then we will be getting the size of the weld, that is H as 885 divided by 90, that will be coming around 9.56 mm. So this is the size of the weld which was asked in the question. We can assume or equate to around 10 mm. We can round it to 10 mm. The size of the weld, that is H. So this is the way how we have to solve the problem from the design of eccentrically loaded welded joint. The first step is to locate the CG, then find the eccentricity value, then to take the effect of load P, that is the primary shear stress tau 1, then the effect of torque P into E, secondary shear stress tau 2, then the resultant shear stress tau resultant using this equation, then equate to the allowable, then find the value of H. So hope you understood, and thanks for watching.